All right, let's get started on this last day of class. A couple things I wanted to point out. Just posted some things in Canvas that you should all be aware of. Let me show them to you real quick here. Let's see, where's Canvas? So here's our Co-17A class. I'll remind everybody there is an evaluation I would really appreciate you all filling out. You can find the link right here. It should take like 5 to 10 minutes. And then if you scroll down a ways below the class recordings and notes to the exam prep stuff, I just posted starting right about, wow, right about here, some practice final material. So there's a practice final exam right there. And then there will be solutions that I will post later after you've all had a chance to look at the final exam and give it a shot. There's also a final review with solutions. There's also a final review from a different instructor from a couple of quarters ago with written solutions and video solutions. So there's lots of review / practice materials. I also think, let me actually click on that to be sure, but I'm pretty sure. Let's take a look at this for just one moment. Yeah. Yes, okay. I do have physical copies of this, so if you would like a physical copy, you're more than welcome to one. Pass them around. You don't have to take one if you want one. Certainly not. So. What to talk about today? Well, I felt like we should probably do a little bit more with optimization. And then also, somebody asked me a horrid L'Hopital's rule question that I feel like we should address more because of how awful it is than because it's really worthwhile. So let me actually start with that, and then I'll talk about maybe the thought process for how you actually solve things. So you might not want to write this down because it is truly awful, but I will write it down and you can choose what you want to do. Let's see, this is Co-17A, the last day of class. And we're going to start off with this problem here. It's the limit as x approaches 0 from the right of cosine of x times the natural log of x divided by the natural log of e to the x minus 1. And whose class is this for? Okay, so, and the prompt says, use L'Hopital's rule to find this limit. And I would just point out, before we use L'Hopital's rule, even though they told us to use L'Hopital's rule, it's still a good idea to check that we can use L'Hopital's rule. So if we plug in 0, you're going to get cosine of 0, which is 1. Natural log of 0, and if you remember the natural log graph, as x goes to 0, you can set them down, science. The natural log graph goes to negative infinity. This is a quick reminder. Here's y equal to the natural log of x. And as the x values get closer and closer to 0, the y values get very, very, very negative. In the denominator, we also have the natural log of 0 because e to the 0 is 1, 1 minus 1 is 0. And just like we said before, the natural log of something that's getting really close to 0 is going to go to negative infinity. So we have an infinity over infinity type. So great, we can use L'Hopital's rule. We're not violating any rules. Always a good idea to check. always a good idea to plug in whatever x is approaching before you start just throwing L'Hopital's rule at a problem. There was definitely one I saw earlier today. It was like the limit as x approaches 0 of sine of 15 pi x over, or like, no, x approaches pi over 2 of sine of 15x over, I don't know, like cosecant of 21x or something like that. And you didn't even have to use L'Hopital's rule at all. You literally just plugged in 0 and got a value. So definitely, before you start doing things, make sure you at least mentally check, if I plug in 0, do I just get a nice number? Or do I get something where I can use L'Hopital's rule? Or something else? All right, so now the first step is not too bad. Limit as x approaches 0 from the right. It's going to be, I'm actually going to do this top product rule out of order. I'm going to do cosine times the derivative of the natural log, which is cosine of x times 1 over x, plus the derivative of cosine times natural log, and the derivative of cosine of x is negative sine of x. So it's really minus sine of x times the natural log of x, divided by the derivative of the natural log of some stuff is 1 over the stuff, e to the x minus 1, times the derivative of the stuff, and the derivative of e to the x minus 1 is e to the x. And that looks pretty terrible. So I looked at that for a while, and I was like, oh, geez. Like, I don't want to try using L'Hopital's rule again right after that. I mean, I could, because, well, actually, it's kind of weird. I think this is still an infinity over infinity form. It's actually positive infinity, because you have a 1 here times a 1 over 0 here. That part's going to give you infinity. That part's going to give you 0. That part's going to give you infinity. But it's kind of gross. I don't want to use quotient rules inside of L'Hopital's rule. So what I did at this point is like, I should check to see if this thing really is going to even exist. So that's when I decided to graph it, because that's really the only way I know how to look at what's happening with this function. So I graphed it somewhere in my tabs up here. There we go. And when you graph it, here's what the graph looks like of the original function, right? Not the L'Hopital's rule version. The original function, the graph looks like that. And so we can pretty clearly see from the graph that as we approach 0 from the right, there's a vertical asymptote somewhere here. But then as we come back over here, we come down, down, down. So x is close to 0. The y values get really, really close to 1. So I'm pretty confident, I'm very confident the limit's going to be 1. Showing it using L'Hopital's rule, on the other hand, is challenging. So here's what I would do first. I would get rid of fractions and fractions, meaning I'm going to multiply the top and bottom by x to get rid of the 1 over x there. So I'm going to rewrite this as the limit as x goes to 0 from the right. On top, I'm going to get cosine of x minus x times sine of x times natural log of x, divided by, I'm going to multiply this fraction by x. So I'm going to get x times e to the x over e to the x minus 1. Oh, you can't see anything I'm doing. Sorry. Jeez. Sorry about that. So I multiply the top by x, multiply the bottom by x. I still have a fraction down here, so I'm actually going to flip and multiply. So I'm going to rewrite this as the limit as x approaches 0 from the right of something terrible, cosine of x minus x times sine of x times natural log of x times, so all of that times e to the x minus 1 divided by x e to the x. And now I had to convince myself that I could still use L'Hopital's rule here. And that's actually more work than you might think. The bottom is certainly going to 0, right? If I plug in 0 on the denominator, I get 0 times e to the 0, which is just 0 times 1, which is 0. And the numerator, okay, yeah. Okay. So in the numerator, cosine of 0 is 1. This part here is problematic because you have x, which is going to 0, sine of x, which is going to 0, times natural log of x, which is going to negative infinity. So for this part, we're going to actually have to check that it actually is going to not infinity before we can say that this times this is going to give us a 0 on top. We need to be going to 0 on top to be able to use L'Hopital's rule again, but it's unclear. We have 1 minus something, we don't know what, times e to the 0, which is 1 minus 1 times 0. And you might think, well, James, it doesn't really matter because 0 times that's still going to be 0. Not true, necessarily. This thing here could be infinitely large. And the 0 thing times an infinity thing is an indeterminate form, meaning you don't know the top of 0 necessarily. So we're going to take a quick trip aside. So a quick aside here. We're actually going to ask, what's the deal with x times sine of x times natural log of x as x approaches 0? We're kind of doing a limit within a limit. It's kind of terrible. It's actually really terrible. Yeah, it's really, yeah. Sorry, it's really terrible. Which part do I want to put on the bottom? Yeesh, yeesh. Let me think for a second here. That's terrible that way. Let's go ahead and put the x on the bottom. So we're going to rewrite this as the limit as x approaches 0 from the right of sine x times natural log of x divided by 1 over x. That's not going to be good either. It's so bad. I'm so disappointed by this problem. This problem is really gross. What did I do there? I did that. That's dicey at best. So let's bring the sign to the bottom as well. So here's the issue. Here's the issue I'm seeing ahead of time before doing the thing. If I leave the sign on top, I'm going to use the product rule. I'm going to get cosine times natural log, and then plus sine times whatever x. And then having a natural log still around is undesirable. So I'm going to instead rewrite this as the limit as x approaches 0 from the right of the natural log of x on top over, I'm also going to bring the sign down to the bottom and get 1 over x times sine of x. Ugh. I'm really not thrilled. So then we try to use L'Hopital's rule for this limit within the L'Hopital's rule problem, which seems even more bonkers. And we get the limit as x approaches 0 of, okay, the derivative of the top is 1 over x. The derivative of the bottom, I guess we're going to have to use the quotient rule for. So it's the bottom. Oh, I could be a little bit smarter. I could think of this part here as x times sine of x to the -1. And the derivative is going to be -1 times x times sine of x to the -2 times the derivative of x times sine of x, which is the product rule. Who assigned this problem? Sorry. 1 times sine of x plus x times cosine of x. Okay, let's rewrite it a little bit. So I'm going to write this as, I'm going to bring this part to the top. So I'm going to have the limit as x goes to 0 from the right of 1 over x on top times x squared times sine squared all over the bottom, which is a -1 still, and a holy smokes, a sine x plus x cosine x. Good times. Okay, I'm going to cancel one of the x's here. And then I'm actually going to divide the top and bottom by x as well. So here's what we're going to get. I have an x sine squared, but I'm going to divide by x. I'm going to have just a sine squared x on top. On the bottom, I have a -1 times a sine x over x plus a 1 times cosine of x. And finally, we can say sine x over x goes to 1. Cosine x also goes to 1, or sorry, cosine of 0 goes to 1. And sine squared of 0 is 0. So we end up getting 0 over -2, which is 0. We're not even done with the problem yet. Okay, but here's the sum up. This limit is 0. The limit of this part here, this in fact does go to 0. I probably could have done that in a somewhat easier way, maybe, but it's truly bad. Now, here's what I want to point out, though. In fact, I'm going to say two other things, which are also true, and I'm not going to show them. You all can show them on your own if you want to. Note as well, the limit as x approaches 0 of x times natural log of x is also 0. And yeah, it is. The limit as x approaches 0 from the right of sine of x times natural log of x is also 0. So what I could have actually done, just so you're aware, is instead of trying to do this stupid thing I just did, I could have said, well, the limit of just that part is 0, right? X times natural log of x goes to 0. You can show it using L'Hopital's rule. In fact, we might as well, since I've said it enough times here. It's just going to be this. The limit is x goes to 0 of natural log of x over 1 over x. Then if we use L'Hopital's rule, we get the limit as x goes to 0 of 1 over x over negative 1 over x squared, which becomes the limit as x goes to 0 of 1 over x times negative x squared over 1, which is the limit as x goes to 0 of negative x, which is just 0. And so what I could have, should have actually said was, hey, since this thing goes to 0, and then I multiply it by sine of x, which is also going to 0, two things going to 0 multiplied together is going to go to 0 times 0. Would have been the smarter way instead of doing all of this stupidity over here. Sorry about that. I thought it was going to be not so terrible. But here's what we finally can get to say. This is a 0 over 0 type of limit. So we can use L'Hopital's rule again. Now we pray. No, I've done this part already. It is gonna work. It's just gonna be really, really gross because if I want to use L'Hopital's rule, yeah, I'm actually gonna multiply out the top before I use L'Hopital's rule. So look at what I've got. I've got cosine of x times e to the x. I've got cosine of x times negative 1. I've got negative x sine of x natural log of x times e to the x, a quadruple product rule. And I've got negative x sine of x natural log of x times negative 1, which is plus x sine of x natural log of x, all divided by x e to the x. Here's the good news. The good news is that in the next step, when we use L'Hopital's rule, the denominator will no longer be going to either 0 or infinity. Because when we take the derivative of x e to the x, we get 1 times e to the x plus x times e to the x, and that's going to go to 1 plus 0, which will be 1, which is not 0. So we're pretty sure the next step is going to result in a final answer, which should be what? What we say the answer is going to be? 1, right? By looking at the graph. Now, if I was doing this question, actually, I might have cheated. I mean, I technically cheated by looking at the answer. But I might have just done like the first step and then said equals 1. Because this is just terrible. But here's how you can get there. Now watch, because it's going to be really, really, really awful. We're using L'Hopital's rule. We have the limit as x approaches 0 from the right. And I'm probably going to need 2 lines to write the entire derivative of the top part. Let's see if I can write here. So I'm going to use the product rule here. So it's negative sine of x times e to the x plus cosine of x times e to the x minus the derivative of cosine is minus negative sine. So that's going to be plus sine of x. Okay. So here we do have to use the quadruple product rule for x times sine of x times natural log of x times e to the x. And I'll remind you that when we do a product rule of many things, it's each thing's derivative multiplied by all the other not derivatives. So it's the derivative of x, which is 1, times sine of x, times natural log of x, times e to the x, minus, now it's going to be x times the derivative of sine, which is cosine, times natural log of x times e to the x, minus, and it's all minus because it's a minus all 4 of these products added together. So it's a minus each one, because the minus sign will distribute. Minus x times sine times the derivative of the natural log of x, which is 1 over x, times e to the x. Finally, minus x times sine times natural log times the derivative of e to the x, which is still e to the x. Plus, now a triple product rule. Derivative of x times sine times natural log plus x times the derivative of sine times natural log plus x times sine times the derivative of the natural log of x. all divided by the derivative of the bottom, which is 1 times e to the x plus x times e to the x. Yeah, exactly. All right, we're almost done, I promise, with this problem. So I'm going to simplify this just a little bit. I really would prefer not to write it again. So here's what I'm going to point out. The x times 1 over x here cancels out. And the x times 1 over x here cancels out. And sadly, I don't think anything else actually cancels out. But I didn't look that closely. So let's see what we're going to get. Now, this final answer is going to also require some liberal usage of knowing some limits already. So I plug in 0, let's see what we've got. Negative sine of 0 times e to the 0 is just 0 times 1. That's going to be 0. So I did that part. Cosine of 0 is 1 plus e to the 0, sorry, times e to the 0 is 1 times 1, which is 1. Dealt with that part. Sine of 0 is 0. Okay. Now, check out this part here. I claimed over here that limit is 0. You can show it. It's just L'Hopital's rule. It's not much worse than this one. So that means if you take this thing that's going to 0 and multiply it by something that's going to 1, it's still going to be going to 0 because 0 times 1 is 0. As long as the thing you're multiplying by isn't infinitely large or negative infinitely large, we're safe. So that part there, I forgot to underline this part here. That part there is going to be minus a 0. But technically, you would have to use L'Hopital's rule to show that the limit of that individual part is 0, which I know is extra terrible. Similarly here, the x times the natural log of x has a limit that goes to 0 as x goes to 0. We showed it right there. And then if you're multiplying it by cosine of 0, which is 1, and e to the 0, which is also 1, you get 0 times 1 times 1, which is still 0. Sorry, I got, yeah. And then this is a sine of x times e to the x. Sine of 0 is 0, e to the 0 is 1. This is a x times natural log of x, which goes to 0, times sine of 0, which goes to 0, times e to the 0, which goes to 1, and 0 times 1 is 0. This limit is also 0 because we said it right there. This is also 0 because you have an x times natural log of x, which goes to 0. And this is sine of 0, which is 0. All divided by e to the 0 plus 0 times e to the 0, which ends up being 1 plus a lot of zeros over 1, which is 1. And oh my God, might be the worst limit I've ever seen. And I've seen a lot of limits. And this is truly, truly heinous. Definitely not a viable test question in any way, shape, or form. Unless they gave you the graph and said, evaluate this limit by looking at the graph. Are there any, and it would be very valid to have questions about this, are there any questions about this particular example? I'm really not sure if this was what the person who wrote this problem expected to happen or what. I have no idea. I'm really like, I have no clue what the person writing this problem was like. This is a great problem. This is not a great problem. But it is kind of interesting. All right, we can be done with it. I can certainly be done with it. So yeah. Let me see where I'm at here. Yes. Cool. So let's look at a couple more optimization problems. Yeah, this is a pretty classic type of problem here. So we wish to design a cylindrical can that can hold, I'm going to try and make the numbers not too terrible. Let's say 100 pi cubic centimeters of volume. Or you can say milliliters, kind of same thing. So 200 milliliters, that's a fairly standard size of a Coke can, or 314. It's about 12 ounces, maybe. Yeah, approximately. Sure. Anyway, we don't really care. We just want the numbers to be not terrible. What dimensions will minimize the amount of aluminum required to make the can? Even though I want to start writing equations, I'm first going to draw a picture of my can. So here's my cylindrical can. And yes, I know Coke cans aren't like perfectly cylindrical because they've got like weird little bumps and ridges and things, but we know it's math. We make broad assumptions about shapes. So we're going to call the height h and the radius r. And those are the two dimensions we're trying to find to minimize what? I know I said I want to minimize the amount of aluminum required to make the can. Well, in this case, we're measuring the amount of aluminum by measuring the surface area, which is almost always the thing. If you're trying to fix volume, you're usually minimizing surface area. If you're trying to fix surface area, you're usually trying to maximize volume. So we want to minimize surface area. Surface area of this cylinder. So here's what I think about for a cylinder. You've got two circles, the bottom circle and the top circle, and those each have an area of a circle, which is pi r squared. So my two circles give me a 2 pi r squared. That's going to be the top and bottom circle, plus the around part. And here's the way I've always imagined this. I like to imagine instead of being a can, it's a roll of paper towels. And I take one paper towel that goes all the way perfectly around the cylinder, and I take it off the sheet of paper towels and unroll it. And what shape do I have? I have you might say a square because some paper towels are square shaped, but we're going to be more general and say it's a rectangle. So this paper towel that is exactly how much area is around the cylinder is going to have a height of h and a length of the circumference of the circle. So this length down here is equal to 2 pi times the radius, which is the circumference of a circle. So the area of the around part here is 2 pi r times h. And that's what we're going to add on over here. And since it's the thing we're trying to optimize, we don't set it equal to any number. That is, if we knew what number it was equal to, we'd be done with the problem. That would be the value of the minimum. Sorry, I'm just looking for things over here. Okay, so then, of course, we want to find our constraint, our limiting piece of information. Well, our constraint is that we want the volume to be 100 pi cubic centimeters. So we want the volume to equal 100 pi. But the equation for the volume is, cylinders are relatively nice. It's the base area, so pi r squared, times the height. We want that to equal 100 pi. So pi. So that's our constraint. That pi times r squared times h is equal to 100 times pi. After this, the processes are all the same. We take your constraint, isolate the easier variable, plug that back into the other equation. Then your equation is a function of one variable. We take its derivative, we set it equal to 0, we find the critical points, make sure it's a minimum, and then we find the thing the question actually asked for, which might be the surface area or might be the dimensions. In this case, we asked for the dimensions. But all those steps are kind of the same every time. You're doing the same things, just the equations are different. So first and foremost here, we're going to, which one's going to be easier to isolate? R or H? Definitely H, right? R has a square on it. I don't want to take a square root if I don't have to. So I'm going to isolate H. So we're going to get h equal to 100 pi divided by pi times r squared. And yes, I should definitely cancel the pi's and say that h is equal to 100 divided by r squared. And then we're going to exactly substitute that in for the only h right there. Another good time that h is the easier one to solve for. It's also going to be the one where you only have to plug it in once, as opposed to plugging it in twice. So now our new surface area equation as a function of just r is going to be still the 2 pi r squared here, plus 2 times pi times r times 100 over r squared. And it's definitely going to be in our interest to simplify this function of one variable before we try to take the derivative. So I would rewrite this as 2 pi r squared plus 2 times 100 is 200 pi, and then one of those r's can cancel out. So I can write it as 200 pi over r, although I still don't feel like I've written it in the easiest way to take its derivative. I should really bring that r up to the numerator and write it as 2 pi r squared plus 200 pi times r to the negative 1 power, because that's going to make it easier to differentiate it in the next step. I'm a big proponent of simplifying your function before you have to take its derivative. It's going to make your life easier generally. All right, so now we are going to take the derivative here. Let me write the function again, just in case this page gets lost here. So the function is 2 pi r squared plus 200 pi times r to the negative 1. And then the derivative here is going to be 2 pi times 2r, so 4 pi r. And then I'm not going to write the plus sign here because I can see that minus sign is going to come down in front and change the sign. So let's make it a minus. Let's see, negative 1 times 200 is negative 200 pi times r to the negative second power equal to 0. And there's a couple ways you can go about solving this from here. One way would be to write the left side as a fraction, get a common denominator, do all that jazz. In fact, let me actually show you both ways so you can kind of see which way you prefer. So here's one way to do this. You can rewrite the left-hand side as 4 pi r minus 200 pi over r squared, still equal to 0. Multiply this part by r squared over r squared. So I'm going to get 4 pi r cubed over r squared minus 200 pi over r squared. And then I'm going to, from the top, first of all, write it as one fraction and then factor out a 4 pi. If I factor out a 4 pi, I'm left with r cubed minus what? What's 200 pi divided by 4 pi? Well, pi's cancel. 200 divided by 4 is 50. So then if we're trying to set something equal to 0, I should say, we're trying to set a fraction or a quotient equal to 0, we really just set the top part equal to 0. So we're going to get 4 pi times r cubed minus 50 equal to 0. Divide both sides by 4 pi. So you get r cubed minus 50 equal to 0. R cubed equal to 50, or r is equal to the cube root of 50. And this is probably not the way I prefer to actually do it, but some people really like keeping everything on one side and doing it kind of the prim and proper way. And this is probably technically the safer, more correct way to do this. But here is something that works just as well. You can say 4 pi r minus 200 pi over r squared equals 0. Bring this to the other side. 4 pi r equals 200 pi over r squared. Multiply both sides by r squared. You get 4 pi times r cubed equals 200 pi. Divide both sides by 200 pi. You get r cubed equal to 200 pi divided by 4 pi. And you get r cubed equal to 50. And you get r equal to the cube root of 50. To me, that feels like less. But either way is fine. Clearly, either way got us to the same critical point. Okay, so now the question. Does this critical value minimize the surface area? Well, I don't feel like taking the second derivative here is going to be particularly nice. Right, taking the derivative, I mean, it's not the worst thing ever. We could probably do it. Yeah, I take it back. We could probably do this using the second derivative. Here's our first derivative. Let's take the second derivative. Let's see. The derivative of 4 pi r is 4 pi. The derivative of negative 200 pi times r to the negative second is going to be negative 200 pi times negative 2 r to the negative third. And before I plug in my critical point, I'm going to make this look more recognizable. It's 4 pi minus times the minus is plus 400 pi over r to the third power. This is actually going to work out great. Because if I plug in the cube root of 50, I'm going to get 4 pi plus 400 pi divided by, you know what, it actually doesn't matter. I should say one more thing. It doesn't matter because if I plug in the cube root of 50 and cube it, is the denominator going to be positive or negative? Everybody. It's got to be positive. But here's why I'm asking the question. I was asking the question because there's no other option, right? If you plug in a positive number, cube root of 50 is certainly positive. It's like 3 point something. If you cube it, it's going to be still positive. In fact, it's going to be 50. But the point here is that when you're plugging this into the second derivative test, we only care if it's positive or negative. We do not care about the value. So if you plug in cube root of 50 here, you're going to get that this is positive. And if you actually plug it in, you're going to get the cube root of 50 cubed, which is just 50. So you end up getting something like 12 pi. But again, we don't actually care. We just care that it's positive because the second derivative being positive means the function is concave which way? Up. And if the function is concave up, then your critical point where the derivative was 0 has to be a maximum or a minimum. It's got to be a minimum. There's no other choice. So that's what the second derivative test tells you. That if you plug in your critical point from the first derivative and you get a positive second derivative, it's got to be concave up, meaning you have a minimum. Or if you get a negative second derivative, it's got to be concave down, meaning you had a maximum. And as long as the derivative isn't too terrible to actually find, I should say, as long as the second derivative isn't too terrible to find, I think this is kind of easier than using the first derivative test. Well, kind of. Because I will point out, doing it this way means you actually have to show your work, whereas you could totally lie your way about the second derivative or the first derivative test. You could say, well, yeah, I definitely checked a number bigger than the cube root of 50, and for sure, my first derivative was positive over here and negative over here. So my function was decreasing then increasing. So I have a minimum. And you all saw me check two numbers, right? Did they watch you do it when you took the test? Right. So if you know something's supposed to be a minimum and you have to check it and you're running low on time, you can do this. You can say, yeah, I know that there's a critical point and I'm supposed to find a minimum, so it's going to be a minimum. Rarely is anyone asking you to find a minimum and have it not exist. And I will say, the only time you couldn't really get away with doing something like this is if your function had more than one critical value. Then you really couldn't do this, and you'd actually have to check. I wish I thought of that when I was a student. I think it would have been like way easier than actually having to check stuff. Are we done? Did we finish the problem? What the problem asks us for? So after you found your critical point and checked it, that's when I would go back and be like, okay, what do I actually need to find? So I go back and read the problem. We want to design a cylindrical can that can hold this many cubic centimeters of volume. What dimensions? I should have underlined that when I was reading it. What dimensions, plural, do we want to have? So we want to find the radius and the height. So we know that the radius is this lovely number here. And let's not use another piece of paper, James. Let's just use our height equation over here and say, well, great. The height is going to be 100 divided by the cube root of 50 squared. And I would leave it like that. But I do want to actually simplify it for you so you can see something interesting. So that's a perfectly good way to leave your answer. But if we simplify it, there's something neat to see. So if I do some simplification here, check this out. Yeah. So I'm going to rewrite this as instead of 100 as 2 times 50 divided by the cube root of 50 squared is 50 to the 1/3 power to the second power, or it's 50 to the 2/3 power. And when you have 50 to a power divided by 50 to another power, what do we do with the powers? We subtract them. So this is really 2 times 50 to the 1/3 power, or 2 times the cube root of 50. All this to say that the height is exactly twice the radius. Or in other words, the diameter of your can is the same as the height of your can, which probably isn't what a Coke can looks like, right? But it is what like a can of refried beans looks like. The bigger cans of beans in the grocery store, if you've ever seen them, they are about as wide as they are tall. And that's I mean, there's also other things to consider when you're designing a can, but one of the things we're certainly taking into consideration is the cost of materials we are using to design the can and using the least amount possible.
Like most of optimizing the surface area ends up being
that is an excellent observation that is often true. It's not always true though. And even if it was always true, you still have to show the work. But yes, it is not, you are not wrong. It is often the case that either the diameter and the height are the same, or the radius and the height are the same. I think if you do this problem, I don't remember actually. I know if you change this problem up a little bit and make it so that it's an open top, like a cup, right, where the bottom has surface area but the top does not, I think you get the radius and the height being the same in that case. I think, but it's been a while, which would be kind of a weird cup because then your cup's really wide and not very tall. Yeah, that actually happens with lots of shapes where you get things into being the same or double each other because of how things work out. All right. So we could do more optimization, but I guess I could ask, is there anything you all are particularly concerned about, have questions about, or anything you'd like me just to talk about in general? And I have one idea. Yeah.
now with this is going to use
No, that's an excellent question. So here's what I would say about limits. First and foremost, read the question. Because sometimes the question will say, use L'Hopital's rule to evaluate this limit. And then you're good to go. Use L'Hopital's rule. But if it doesn't say that, and it just says maybe just find the limit using whatever method you care to use, then you have to check something. So I would say after you've read the question, if you're still taking a limit, plug in whatever x is approaching. As you always should with a limit. Because if you get a value, you're done. For example, what was the line I just saw the other day? I saw something like the limit as x approaches 0 of e to the x minus 1 over cosine of x plus e to the x. That wasn't exactly it, but close enough. And here, if you plug in 0, what happens? We get e to the 0 minus 1 over cosine of 0, which is 1, plus e to the 0, which is also 1. And you're going to be getting 0 divided by 2, which is just 0. And that's it. You're done. 0 is a real answer. So make sure you plug in whenever x is approaching. And then if we get an indeterminate form of the right type that is either 0 over 0 or some type of infinity over some type of infinity, then and only then you can use L'Hopital's rule. Should you? Probably. There are rare exceptions. I don't think your instructors are going to try to trick you into accidentally using L'Hopital's rule in a case where you could, even though you shouldn't. I tried to give an example of this a couple of classes ago. An example where you shouldn't was something like, no, it's not. I shouldn't even say it. Like it's just if you see this, then I would say it's the safe bet to just go ahead and use L'Hopital's rule right away. But I will tell you, right, it has to be one of these. And then if you have one of the other indeterminate forms, if you have something like an infinity times a zero, or an infinity minus infinity, or a 1 to an infinity, or an infinity to a 0, or a 0 to a 0, you have to do some rewriting. So specifically, for an infinity times 0, something like the limit as x approaches 0 of sine x times natural log of x, just to bring that lovely one back already, that you have to bring one of the things to the bottom. What's the thing we never bring to the bottom? Never bring natural log of x to the bottom. I cannot think of a time I've ever been able to do that, and it was the right choice. You would rewrite this as the limit as x approaches 0. Well, actually, so here's how you could start rewriting it as natural log of x over 1 over sine of x. But specifically with trig functions, when you bring them to the denominator as the reciprocal, you should almost rewrite them as whatever the reciprocal trig function is. I don't want to take the derivative of 1 over sine. I want to take the derivative of cosecant. So I'm going to write this as the natural log of x over cosecant of x. Now it's an infinity over infinity form, and I can use L'Hopital's rule. Another example would be something like the limit as x approaches infinity of x squared times e to the negative x. That's also an infinity, right? X squared is getting infinitely large. E to the negative x, which is going to e to the negative infinity, is getting closer and closer to 0. So that's definitely an infinity times a 0. And we would rewrite this as the limit as x goes to infinity of x squared over not 1 over e to the negative x, but just e to the x. And then you use L'Hopital's rule twice because it's an infinity over infinity type. So for these ones where you have things multiplying infinity times 0, you're always bringing one of those factors down to the bottom as the reciprocal. And I'll be real frank, we don't usually see a whole lot of these, but if you do, it's almost always a case of having to get a common denominator. Usually it's going to be some sort of fraction minus some sort of fraction, or one of them will be a fraction, and you have to get a common denominator. There's not a lot of good examples, so I don't have one off the top of my head just to write down. On the other hand, there's plenty of examples of ones like this. So for the last indeterminate form, which it is practically a guarantee. You will see at least one of these, probably at least two of them, to be honest here. But if you can see like a 1 to the infinity is something like the limit as x approaches 0 of 1 plus x over 2 to the 3 over x power. Whoops, sorry. Or something like the limit as x approaches infinity of 1 plus 5 over x to the x power. These are both examples of 1 to the infinity type of limits. Or a 0 to the 0, a real classic. The limit as x approaches 0 of x to the x, or the limit as x approaches 0 of sine of x to the x. And what was the last kind? Infinity to the 0 is always kind of funky. The limit as x approaches infinity of x to the 1 over x. All of these types of limits that are indeterminate forms have something in common. They all are somewhat exponential in something, right? You have something to a power of something. And for each of these, you have to do the logarithm thing. You have to take the natural log of your thing, bring the power down in front, then divide by reciprocal, then take the limit, then get an answer. And then remember that your answer is actually e to the thing you found. Let's do one of these. Let's do this one. So if we wanted to find, let me pass out the attendance form before I forget completely. Where did I put it though? That's the question. It's always hiding. Somewhere, somewhere, somewhere. You start working on that limit while I find the attendance form. Where did I hide it from myself? There it is. I found it. So for this limit, as x goes to infinity of 1 plus 5 over x to the x, I probably prefer to think of it, bless you, as the limit as x goes to infinity of e to the natural log of 1 plus 5 over x to the x. And then I'm going to rewrite that as e to the limit as x goes to infinity of the natural log of 1 plus 5 over x to the x. And then we're just going to look at the part in brackets. So whatever's in the brackets there, we're going to fill it back in up there. So our empty square is equal to the limit as x goes to infinity of the natural log of 1 plus 5 over x to the x. And there's always two steps we need to take before we can use L'Hopital's rule for these problems. You bring this power down. Well, I should say there's sometimes two, sometimes one. You bring that power down in front. You get x times the natural log of 1 plus 5 over x. I'll point out that this is an infinity times 0 type. You have x going to infinity. You have the natural log of 1 plus 5 over x going to the natural log of 1 plus 0. And the natural log of 1 is 0 itself. So this is really an infinity times 0 type. Which again, we can't use L'Hopital's rule for yet. We still have to write it as a fraction. So it's 0 over 0 or infinity over infinity. We're never going to bring the natural log to the bottom. We're going to write this as the limit as x goes to infinity of, you write this part on your own. This is the part where I see the most mistakes happen. I'll do you a favor. I'll write the top part. And when you've written the bottom part, look at me or towards the board. All right. That x comes down to the bottom, not as x, but as its reciprocal, 1 over x. It has to happen that way. And now it is an indeterminate form where we can use L'Hopital's rule because the top is going to 0, the bottom is also going to 0. So now finally we get to use L'Hopital's rules and say it's the limit as x goes to infinity of the derivative of the top. So this is probably not the best way. I'm doing something here that's probably something that I just like and is not good other than that I like it. But I think it's probably better if you actually write this part as 1 plus 5 times x to the negative 1 instead of as 1 plus 5 over x. Similarly here, it's probably better to write that as x to the negative 1 because it's easier to take the derivatives that way. I just like writing it like this because I just do. So taking the derivative of the natural log of all that stuff, it's going to be 1 over all that stuff times the derivative of that stuff, which is going to be the derivative of 1 plus 5x to the negative 1, which is going to be 0 plus negative 5 times x to the negative 2. Over the derivative of x to the negative 1, which is negative 1 times x to the negative 2. And this happens a lot for these problems. You can cancel something out really nicely. What cancels? X to the negative 2 divided by x to the negative 2 is 1. So that goes away. And now we're left with something that's not terrible at all. We have the limit as x approaches infinity of 1 over 1 plus 5 over x times negative 5 divided by negative 1. As x goes to infinity, 5 divided by x gets really, really small. So you have 1 over 1 plus 0, which is just going to be 1 times -5 divided by -1, which is 5. And then our final answer is e to the 5th power. So one more time, I'll say each of these limits would require a similar process where you have to do e to the natural log of the thing, and then just look at the natural log of the thing, and then bring the exponent down in front of the logarithm, and then bring it down to the denominator as the reciprocal, and then apply L'Hopital's rule, get an answer, and then your actual answer is e to that answer. But you should practice one. Like each of these problems worth practicing. You should try each of these on your own. They're all problems that could very, very, very potentially be on your final exam. I would not feel bad about putting any of those problems on your final exam. Yeah, none of them. They're all perfectly good problems. That was a very long answer to your question about L'Hopital's rule. But it's a good question.
Going to find a minimum or maximum probabilities in the word problem.
In a word problem. Sure. So like an optimization. Well, so because when I hear a word, I'm thinking like an optimization problem. Is that what you mean? Or not exactly?
It's not necessarily Mendel's find out. But it's like finding a minimum and max using the word problem.
I guess I'm not really, because I'm thinking like graphically we find minimums, maximums all the time, but in a word problem, I'm having a hard time thinking about like, I mean, did he post a practice final?
Yeah.
Is there something like that on the practice final?
Mm-hmm.
All right, let's take a quick look. Also, if I have a chance, I will gather the practice finals from your various instructors and post them all on Canvas so that you can look at each other's practice finals, because sometimes that's useful. So let's see here. I'm going in the wrong place. So let's go look at Alameda's class. Go. I assume it's in files somewhere. Let's see. Exam prep was most likely. I'm assuming it's, do you know which of these it is? Is it the final practice or the final study guide? Okay. Let's take a look here. Got some limits, more limits, more. We'll try this one too, because I think that one's worth doing and it's a little bit of a pain. More limits, lots of limits. Wow, limits all over the place. That's a whole lot of limits. So I will say probably not all of these are going to be L'Hopital's rule. Most of them will be, but some of them will not be, most likely. Implicit, related rates. Is this the one we're kind of looking at? Okay. Maybe this one. It's okay if it's not. I'm seeing max min. Absolute max, absolute min. That's the end of the practice test. So the thing is, typically with word problems, you're only asking for either a maximum or a minimum. Whereas with these other problems, which are kind of more, although you're not actually being asked to graph it, that's where you're finding maxima and minima. So we should go through problems like this, yeah. Let's go ahead and look at a couple of these because I do think it's worthwhile to remember the difference between finding absolute versus local. So let's look at this last problem here. Do I want to change it at all? Kind of. All dizzy. Sorry, one sec. So yeah, let me write this down. So our function is 2x cubed minus 3x squared minus 12x plus 10. And we're on the interval from -2 to 2. We want to identify the absolute maximum value and absolute minimum value. Okay, sorry, I know you can't see what I'm writing. Okay, first step in this process, find your critical points. So critical points, we're going to take our derivative, which is going to be 6x squared minus 6x minus 12, set it equal to 0. We're fortunate here in that each of the components has a factor of 6. So we can factor out the 6, left with x squared minus x minus 2 equal to 0. And then we can factor that further as x minus 2 times x plus 1 equal to 0. And then our critical points are x equal to positive 2 and x equal to negative 1, which both happen to be in the interval. Now I want to point out, if instead I had made up a different problem and said the interval was, say, 0 to 10, we wouldn't use both of those critical points because negative 1 isn't in the interval. So definitely be careful when you're finding absolute maxima and minima on a closed interval, which is almost always, whenever you're finding absolute maxima and min, it is almost always on a closed interval. Make sure that your critical points that you're going to test actually live inside of the interval you're talking about. If they don't, they're no good. So for this interval here, x equals 2 is fine, but x equals negative 1 is not, if that was the interval in question. We'll look at this one at the end after we do the actual one here. So for this problem, after we find our critical values, then we're just going to plug all of our critical values and all of our endpoints into the original function. This problem happens to have one of the critical values the same as an endpoint. That's totally fine. So we're going to find the original function f of 2, f of negative 1, and f of negative 2. F of 2 is going to be, so we have to go back and plug into the original function. So it's going to be 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 10, which is going to be 2 times 8 minus 3 times 4 minus 12 times 2 plus 10. So 16 minus 12 is 4. 4 minus 24 is negative 20. Plus 10 is negative 10. And then f of negative 1 is a little easier. So the nice thing about putting in negative 1 is negative 1 to an even power is 1. Negative 1 to an odd power is negative 1. So we're going to get 2 times negative 1 cubed. So that's just 2 times negative 1. Minus 3 times negative 1 squared, which is 3 times positive 1. Minus 12 times negative 1 plus 10. That's going to be negative 2 minus 3 plus 12 plus 10. That's a negative 5 plus 12 is 7 plus 10 is 17. And finally, plugging in negative 2, 2 times negative 2 cubed minus 3 times negative 2 squared. You don't have to show as much work as I'm showing. I'm just making sure that everyone's seeing all the steps. But if you know that 2 times negative 2 cubed is going to be negative 16, just write that. Don't write all the steps you need to write, or that you could write. So we're going to get negative 16, minus 3 times positive 4 is minus 12, minus 12 times minus 2 is plus 24, plus 10. That's going to be negative 28 plus 34, which is going to be 6. So there's your absolute maximum. There's your absolute minimum. Make sure we read the question carefully. The question asks us to identify the absolute maximum value, meaning the y value. So the absolute maximum value is negative is positive 17. And the absolute minimum value is negative 10. Be careful with these questions. The question could have just as easily asked, where does the absolute maximum and absolute minimum occur? And the where would be x equal to negative 1 and x equal to positive 2. So if they ask for the value, it's the y part. If they ask for the where it is, it's the x part. To be safe, here's how I like to answer the question. I would have said absolute maximum value is f of -1 equal to 17. That tells you the where and the value at the same time. Same deal here. This would have been f of -2 equal to -10. Just read the, I mean, I'm going to say it as many times as I can. Read the questions carefully. Read the questions carefully. What should you do? You should read the questions carefully. Read the questions slowly and carefully. You're going to have 2 hours to take the test, right? That's how long your finals are. So it's usually more than enough time. Most of your teachers probably are designing tests that they envision you will finish in like an hour to an hour and a half. Probably. So there should be enough time to go to read each question as slowly as you need to so that you can see every little detail. You don't need to rush through the reading of the question. You need to slow down the question to make sure. And I mean, I will admit, I'm prone to making that mistake too. I was helping someone just the other day with a Weber problem where I was like, oh yeah, it's this. I've seen this one before and read the question really fast and then tried to find the answer. Like, I'm doing something wrong here. And then I went back and read it. I'm like, oh, the question actually said something very different from what I thought it said. So even if you think you know what the question says, still take the minute to read the question, please, for yourself. Just to go off what I was thinking about the other one, if instead my interval was from 0 to 10, with f of x equal to 2x cubed minus 3x squared minus 12x plus 10, and critical values of x equal to 2 and x equal to -1, we wouldn't use x equal to -1 because it's not in the interval, and then we would check f of 0, f of 2, and f of 10. F of 0 is super easy. It's 0 minus 0 minus 0 plus 10. F of 2 we already found. It was -10. And f of 10 is, I picked 10 because 10 is relatively easy, because 10 to a power is just some number of zeros after 1. So we get 2 times 10 cubed, which is 2 times 1,000, minus 3 times 10 squared, which is 3 times 100, minus 12 times 10 plus 10. That's going to be 2,000 minus 300 minus 120 plus 10. That's going to be 1,700. -120 plus 10 is -110, which is going to be 1,590. So clearly, that's my absolute maximum. That's my absolute minimum. If that was the interval instead of the other one. In contrast, if the question gives you a function and asks for relative extrema, it's an entirely different process. So, how not nice do I want to make this next question? Not that not nice. Sure, but let me look at what he had. Yeah, okay, that's what I thought. I'm gonna change it a little bit. So let's say that we want to find and classify, meaning tell me if it's a maximum or a minimum, all relative extrema, which is plural for max and min, of f of x equal to x times the square root of 9 minus x squared. There's something important about this function that you need to know. It's got a very limited domain. The domain here is from -3 to 3. The biggest x can be is 3. If x is any bigger than 3, you have 9 minus a number bigger than 9 and the square root of a negative, which is not real. Same deal if x is more negative than -3. It's usually not concerning when you're finding the critical points for the first derivative, but for problems like this, if you had to actually graph this and find like the concave up, concave down stuff, you typically get critical points for the second derivative that actually aren't critical points because it's like you end up getting like 5 as a critical point, which isn't in the interval, so you ignore it. So just be a little bit careful if you see something like this. I mean, I said a lot. Just be a little bit careful for this. Just be careful for the whole thing, right? Be careful. But don't go too slow. Okay. So let's find the critical points. Oh, so first of all, before I do that, I should probably write this as x times the 9 minus x squared to the 1/2 power. So it's easier to take the derivative using the product and the chain rule. So my f prime of x is going to be 1 times 9 minus x squared to the 1/2 plus x times the derivative of that. The derivative of some stuff to the 1/2 power is 1/2 times your stuff to the negative 1/2 times the derivative of the stuff, which is 0 minus 2x. Now, for problems like this, where you've used either the product or the quotient rule and you're trying to find critical points, you're always going to have to do some sort of algebraic factoring to be able to actually simplify this in a way so you can see what the critical values are. There's no way around it. You have to factor here. So looking at both of these pieces, the 1 times 9 minus x squared to the 1/2 and the x times 1/2 times 9 minus x squared to the negative 1/2 times negative 2x. A couple things I see. First of all, the 1/2 times the 2 is just 1. So I'm going to ignore those or cancel them. And then I see that each of these pieces, actually, let me rewrite this. Let me do myself a favor here. 9 minus x squared to the 1/2. You have an x times a negative x, so it's minus x squared times 9 minus x squared to the negative 1/2. And then you're going to factor out, you have a common factor, but it has different powers. So you're always going to factor out the lesser of the two powers. Just like if you were factoring 5x cubed plus 15x cubed plus 5x to the 7th. You factor out a 5 because it's the smaller of the two things, it's the common factor that's smaller to them. And you factor out the x to the 3rd, not the x to the 7th, because the 3 is the smaller of the two powers. And you're left with 3 times x to the 0th plus x to the 7 minus 3 is 4. And when you multiply that back through, oh yeah, you get exactly 5x cubed times 3, which is 15x cubed, and 5x cubed times x to the 4th, which is 5 times x to the 3 plus 4 is x to the 7th. So in the same sort of way down here, although it's a little bit wonkier, we're going to factor out the 9 minus x squared to the negative 1/2. And I want to really, really stress here. When I factored out the x cubed up here, it's like I was subtracting 3 from the power. From either here or here, right? 3 minus 3 is 0, x to the 0 is 1. 7 minus 3 is 4. I got x to the 4th. The same thing is true here. If I'm factoring out something to the negative 1/2, it's like I'm subtracting negative 1/2 from the power. So if I subtract negative 1/2, it's really like I'm adding 1/2. So if I do 1/2 minus negative 1/2, I get 1. I get 9 minus x squared to the 1st power. Do a quick mental check. If you multiply that by that, you add the powers, and negative 1/2 plus 1 is positive 1/2. And then over here, it's even better. We're just going to get minus x squared because this whole thing was exactly what we factored out. Simplify a little bit. In the brackets, 9 minus x squared is 9 minus 2x squared. And then if I multiply by something to a negative power, I'm almost always, whoops, I said 9 minus 2x squared. I did not write it. Sorry. And have something to a negative power, I would almost always rewrite it as that same something in the denominator to the corresponding positive power. And we're going to set that equal to 0 / undefined. Which I'm not really worried about, but I feel like I shouldn't just not say it because technically, if you're finding critical points, it's points in the domain where the function, oh, this is going to be interesting, where the function is either having a 0 derivative or a 0 or an undefined derivative. So here, setting the top equal to 0, I'm going to get some not lovely critical points. I'm going to get 9 equal to 2x squared, 9 over 2 equal to x squared. So x is equal to plus or minus the square root of 9 over 2. Yeah. Okay. 9 over 2 is 4.5, so I'm getting the square root of 4.5, which is a little bigger than 2. So like plus or minus 2 point something. And then technically, if I set the denominator equal to 0, if I set 9 minus x squared to the 1/2 equal to 0, my solutions are going to be x equal to 3 or negative 3. But, well, this is where you get to have an argument with someone. We'll talk about it in the end here. So let's look at our first derivative number line. Now, normally, I would draw this. It's not what I would draw here, because my domain isn't everything from negative infinity to infinity. My domain is everything from negative 3 to positive 3. And then here's my plus square root of 9 over 2. Here's my minus square root of 9 over 2. This is also why it's super duper duper important to have your derivative fully factored. Which I guess I don't technically actually have it fully factored, but I'm going to live with it anyway. Because we have to test each of these 3 intervals to see if the whole thing is positive or negative. Ugh. Okay. There aren't really great numbers to pick here, which is too bad. Fortunately, there's a silver lining. The denominator, being a square root of something, square roots only give you what kind of numbers? Positive, right? Square root of 9 is never negative 3, always positive 3. Square root of 16 is positive 4. So the denominator is always positive, so we really have to worry about the numerator. So if x is close to 3, almost 3, not quite 3. Almost 3 squared is almost 9. Almost 9 times 2 is almost 18, which is way bigger than 9. And 9 minus 18 is definitely negative. So it's going to be negative over here because the bottom's positive. In here, we can pick something easy like 0 or 1. 9 minus 2 times 1 squared is 9 minus 2, which is 7, which is positive. The bottom's always positive, so we're positive in here. And finally, over here in the same sort of way, right, since we were squaring x, it actually didn't matter if it was positive or negative. So I pick something like negative 2.5. That's terrible. Negative 2.5 squared. I don't know what that is, but I know that, no, I really don't. This is not good, right? I'd be like, well, it's close to 3. Close to 3 squared is close to 9. And then 2 times that's way bigger than 9. So it's still going to be negative over there. I don't love that. It's not excellent. But we do now know that our function is decreasing, then increasing, then decreasing. So according to the first derivative test, we have a relative minimum at x equal to negative root 9 over 2, because the function went decreasing and increasing, right? And we have a relative maximum at x equal to positive root 9 over 2, because we went from increasing to decreasing. I sigh because let me show you what this function looks like. Let's see, it has intercepts at negative 3 and 0 and 3, and it's decreasing, and then increasing, and still increasing, and then decreasing. And there's like my relative max, my relative min. And the reason I'm sighing is because some people would probably try to argue that that is a relative minimum, and that that is a relative maximum. I personally, and most textbooks would agree, it is not, because we define relative extrema to be bigger than all the things next to it, and there has to be stuff on either side of it to be defined on. And since this isn't defined on that side, you can't talk about it being a relative minimum or maximum. But other people make up weird definitions, so I don't think that's something you can worry about, but I felt like I had to say. So I would say, don't worry about this. I don't think any of your teachers are concerned about this, but all fun. All right, that's all for today. Definitely check out the things on Canvas. There's lots of practice material to look at. I will also get whatever practice exams there are from the other instructors and post them on campus as well. So if you're not in Alameda's class and you want to look at his school, if you're not in the other two guys' classes and you want to look at theirs and they have them, also cool. I've got office hours tomorrow. Well, right now, actually, over in CAD as usual. And then starting tomorrow, all my office hours are in the library. So if you want to come see me, I'll be in the library. And they're posted on Canvas in like one of the last couple of announcements I made. All right, good luck on your finals. I hope you all do well. I hope you all have a very nice summer. If you're taking summer subject classes, I'll make a post about that as well. You're very welcome.
You guys spent like an hour and a half and we gave up. I was like, it's not happening.
No, I started working on I looked at it briefly last night. I was like, this is